Hi kids, this important video is on um, defining the relationships between two variables. In other words, figuring out how changing one variable will impact the variables that are around it. So the relationships between variables matter, and the reason is because one of the main goals of this physics class is that you students should be able to explain the past and predict the future. You should be able to come to a greater understanding of how all of the things around us are connected to all the other things around us, and how making one little change actually can impact lots of surrounding variables and situations in your world. In order to be able to do this, we have to figure out specifically how changing one variable impacts other variables. This connection between two variables is called a relationship, and you'll find in a later video that these relationships are actually the building blocks of equations. There are lots of different possible relationships between variables. We're only going to really focus on 3 in this class, but you'll probably learn about other ones in your math classes, and you should realize that you can apply any relationship that you learn to equations down the road. In general, we want to know if increasing one variable makes the other variable stay the same, increase, or decrease, and by how much that other variable is going to be changing. So the first thing I want to acknowledge is that not all variables affect all other variables. Sometimes two variables just don't have any kind of relationship with each other. And that means that when you change one, nothing really happens to the other. For example, my height is not related to the color of my shirt. Tomorrow I'll probably have the same height that I had today, and I might have a different color shirt on. If I have a red shirt, that doesn't mean anything about, if you look around this classroom wearing a red shirt, doesn't mean anything about your height. So those are two variables that are not related to each other. And we may discover over the course of this class, we run an experiment and we change something and nothing happens to a different variable. That's okay. Not every variable affects every other variable. However, in many cases, there will be a relationship between two variables. So when you change one, the others will be changing. We're going to be talking specifically about 2 of these, and the first is known as the linear relationship. You should know that linear can also be described as direct or proportional. Sometimes you may have heard those terms in math classes. They all mean the same thing for our purposes, and that meaning is that when you increase the value of one variable, the other variable that you're interested in is going to go up by the same percent. Conversely, of course, if you decrease the value of one variable, that means the other variable is going to be decreasing by the same percent. Some examples of linear relationships: shoes and people. If I double the number of shoes, I did that probably doubled the number of people in my classroom. Or if I take out half of the people, then I'm going to have half as many shoes. You could also say this about happiness and jelly beans. The more jelly beans you get, the happier you are, and vice versa. If I made a data table with some perfect data showing a linear relationship, it might look something like this, right? No people, no shoes. One person, 2 shoes. If I double the number of people, I go from 1 to 2. I'm going to double the number of shoes, right? If I quadruple the number of people from 1 to 4, going to quadruple the number of shoes as well. So this is kind of like a perfect ideal world data set for linear data. So of course, real world data seldom looks as tidy as that last data table that we looked at. It's usually a lot messier. So let's look at like another data set here, jelly beans versus happiness. Start off with 2 jelly beans, and maybe you say my happiness is a level 6 out of 100. And then if I double the jelly beans, now you're 26 out of 100. So you can see that it's going up. As I give you more jelly beans, you're getting happier, but it's hard to tell if this is linear or not, because I can't tell if we're going up by the same percent. So it would be nice to have a tool that lets us see through all of this uncertainty, and that tool, of course, is a graph. Usually when I ask students to make a graph of data, they make something like this, and I'm calling this a bad graph of data. It's not actually terrible. There's a few good things in there. I've noticed that there's a scale on both axes, things are labeled, the data points are in the right spot. You've got a pretty good range, right? You've got the graph is stretched out through this whole graph, and that's actually really good. But the thing that makes this not a good graph is that line that's connecting all of those data points. that line actually has no real physical meaning at all. It doesn't make any sense that your happiness is going to go up a lot more between 1 and 2 jelly beans than it does from 3 to 4. So I would call this a bad graph of the data because I don't want to see that line connecting my data points. So let's talk about how to make a better graph of the same data. We're going to do a lot of the same thing, set up the scale, carefully plot our data points on that scale, but this time, instead of connecting those data points, we just want to take a minute and think about what is the overall trend of this data. Is it going up? Is it going down? Is it curving? And if I asked you that question, with these 4 data points, hopefully you would realize that the simplest possible solution to this is just a line that's going to go up and to the right in my graph. This line is known as the best fit line, and it is the simplest line or curve that shows the trend of the data. So this line lets me kind of take into account all the errors and uncertainties in my individual data points to show simply the overall trend of the data. Now, if the simplest line or curve that matches my data is a line, then you have a linear relationship. So even though we couldn't really tell that from the individual data points on the data table, when we make a graph, we can now predict that this will be a linear relationship. What do you think the slope of this line tells you? If you thought about that a little bit. Well, if you look at the points on the graph, you'll notice that for every 1 jelly bean, the happiness goes up about 10. So the slope is 10 over 1, rise over run. And it kind of tells you that you get 10 happinesses for every 1 jelly bean. In math class, you may have made an equation out of this, right? Y equals 10x. Of course, in this class, we aren't using x and y. We look at our axes. We have happiness on the y-axis, and we have jelly beans on the x-axis. So really, the equation we could make out of this is h equals 10j. That shows me that my happiness is equal to 10 times the number of jelly beans that we have, give or take, okay? It's approximate. So that equation actually has some real meaning. It really describes the happiness of a person as a function of the number of jelly beans that they are given. So the second important relationship we're going to be using a lot in physics class is called an inverse relationship. And you may have seen this in math class before. It's kind of the opposite of your linear. When you have an inverse relationship between 2 variables, when one of them goes up, the other one goes down by the same proportion. So one doubles, the other halves. And of course, if you decrease the value of one variable, the other variable is going to be increasing by the same proportion. So for example, distance driven and gas left. The more distance you drive, the less gas you have. The more gas you have, the less distance you've driven. So that would be kind of the relationship that we're talking about above, the inverse relationship. If I were to make a data table, an ideal data table with inverse relationship, maybe between massages and stress, for example. So if you got 2 massages, you have level 100 stress. But if you double the number of massages, now you get 4, you have half as much stress. It goes to 50. If you instead of doubling, you triple, so I go from 2 massages to 6, now my stress is 1/3 of what it was before, so it went from 100 to 33. So this would be an ideal data table for an inverse relationship. I'm going to go ahead and graph this ideal data just to show you how it looks on a nice clean graph. So this is the stress versus massages we were just talking about a minute ago on a graph, and you'll notice that when you make the best fit line for an inverse relationship, it's actually not a line, it's a curve. That data is clearly not staying in the same line. So inverse relationships actually make a nice curve on a graph that looks just like the curve that you see in front of you. And if you look at 2 data points on the graph, when one data point is doubling, the other one is halving. So when we go from it looks like about 4 massages to 8 massages, our stress kind of went from 50 to 25. So that's what you notice when you look at the individual data points on the graph. Now, unlike the other graph, this one doesn't actually have any intercepts. those lines are going to approach those axes, but they're never going to cross. And I'm not going to go into it right now, but I would think that some of you guys might be asking, what does that mean? What does the lack of intercepts on this graph tell you? It's an asymptote, or something that never crosses those axes. If you want to try to figure that out and come talk to me, I would love to hear your opinion about why this graph does not have any intercepts. So a quick summary of what we've covered in this lecture. Mathematical relationships, specifically linear and inverse, are going to be used to help us explain the past and predict the future. And if two variables have no mathematical relationship, you can't use one to predict the other. But if they have a linear relationship, when one of them changes, the other will change by the same amount, same percent, not the same amount, sorry. And if two variables have an inverse relationship, when one of them changes, the other will change by the reciprocal amount. So when one triples, the other one will 1/3. Thanks for listening.